In this presentation, we are going to show you the data that we have been collecting from two MultiPACK supermarkets. We are actually focusing on the two Italian supermarket sites developed within the project. So first of all, what is a MultiPACK unit for supermarkets? It's a fully integrated unit which is able to provide refrigeration, heating and air conditioning. It's based on carbon dioxide as the refrigerant, and it is adopting the state-of-the-art technology, including parallel compression, overfed evaporators, and ejectors for vapor precompression and liquid recirculation. The units developed within MultiPACK are suitable for the South European climate. They have integrated heat pump functionality to provide all the thermal service required during the winter time, and they provide cooling and dehumidification with direct expansion. These units, they are scalable and adaptable to different load ratios and to different design of the heating, ventilation and air conditioning system. And finally, they are fully instrumented for performance monitoring. This is the data acquisition system that has been developed specifically for this project. So we have different sensors in the unit measuring temperature, pressure, mass flow. We have also power meters at each compressor rack. We measure the status of compressors on the valves, the liquid level, and the frequency of the frequency converter. All the signals are converted into a Modbus and collected in a data logger, which then sends the data to a storage in the cloud. From the cloud, we can download data that are used to build up the MultiPACK database, but they can also, through modeling, generate reports. The Italian sites are located in central Italy. The first one, which was installed, it's in Rome, and the other one is in the north of Italy, in the town of Trento. These two locations have different climatic conditions, and in this graph you can see the temperature profile for both locations, and you can also see that it's very cold in winter in Trento, and it's very hot in summer in Rome. These two sites have also different load ratios, so the demands for refrigeration, heating, air conditioning, they are completely different, and this is also going to impact on the performance of the system. The sites are different, but also the building types are different, and in particular, the site in Rome is a residential building, so the supermarket is in the ground floor of a residential building located in the city center of the town, while in Trento, the building is an isolated industrial type building, so different locations, different type of buildings, and also different indoor heating and cooling system. In Rome, we have an air handling unit, while in Trento we have a peculiar system which is made of fan coils located hanging from the ceiling of the supermarket, and we will go into detail of this specific installation. This is the MultiPACK unit in Rome. It's a booster system, so we have medium temperature and low temperature compressor racks inside the same circuit. Of course, we have parallel compressors, here indicated as auxiliary compressors. We have the expansion via ejectors. Ejectors can remove the vapor from the receiver, which is located in the suction on the medium temperature compressors, but also recirculate the liquid if any liquid coming from medium temperature cabinets is present at the bottom of this receiver. The unit is serving low temperature and medium temperature evaporators, and it's also serving the air handling unit. In the winter time, we have direct flow of CO2 from the discharge line of the compressors inside the air handling unit, and in the summertime, we can expand CO2 after a gas cooler inside the cooling coil of the air handling unit. We have an additional outdoor evaporator, which can work as an additional heat source to to feed the heat pump functionality in the winter time. This is an example of the operating conditions in Rome. We have a summer day on the left and a winter day on the right. You can see that the peculiarity of the Rome system is the fact that the air handling unit is operating only during the day, so when the supermarket is open. During the day, you can see in the summer on the left hand we have transcritical operations here in the central part of the day, while operations are subcritical in the night. On the right hand, winter operations, you can see that the air handling unit heating mode is switched off during the day, and in this situation the gas cooler pressure is increased to recover it and to heat up the supermarket. And here we can also see the suction of the auxiliary compressors, which are working as a heat pump in the heat pump functionality, and so the evaporation pressure of the outdoor evaporator depends on the outdoor temperature. Here we have the average values, the maximum and minimum values in the summer and in the winter. This is the unit which is located in Trento. Again, we have a booster system with medium temperature and low temperature compressor racks inside the same circuit. Again, we have the parallel compression, and the expansion is performed by means of two-phase ejectors. The loads are represented by the medium temperature cabinets and the low temperature cabinets. On the other hand, the unit is also serving the air conditioning and heating system. Here we have some fan coils which are hanging from the ceiling of the supermarket. This is the peculiarity of this site. The heating and cooling is performed by fan coils inside the shop, directly inside the shopping area, while there is also a small air handling unit. The gas cooler is located, of course, outdoor, and the evaporator for the heat pump functionality is integrated in the same frame of the gas cooler. This is an example of indoor unit of the Trento supermarket. So it's a coil which is hanging from the ceiling and which is directly fed by the hot CO2 from the compressor discharge line during the winter time, and by the expansion of CO2 after the gas cooler during the summer season. So in the winter season, we have hot CO2 entering here the coils at a temperature which is between 80 and 100 degrees, and it's flowing back to the unit at 35 degrees. That's depend on the ambient temperature, internal ambient temperature. In the summertime, the CO2 flows inside the coils at the saturation temperature of the receiver, which is about at 5 degrees, and it flows back to the intermediate pressure receiver. Here are some examples of winter operations. So in the winter time, you can see that the pressure is always transcritical. This is because heat recovery is always operating. And we can also see that the evaporation temperature of the outdoor evaporator can go as low as minus 10. Here you can see this blue line, and it's lower than the saturation temperature of the receiver, which is much higher here. And this is because of the outdoor temperature, which is in this case quite low. We can also have an idea of the loads here, where we can see that the heating demand is as high as 100 kilowatt, and this of course corresponds to a high energy power input to the auxiliary compressors. During the summertime, we can see again operating parameters, loads, and electrical power input to the compressors. We want also to show you what's the effect of the superheating on the performance of the system. This is an experiment that we have carried out during a winter day in Trento. what we have exactly done is decreasing the superheat, which was initially at 8 degrees. Here you can see the set of the superheat, and we have decreased it to 4 and then down to 2 degrees and then back up to 8 degrees. At the same time, we have progressively increased the evaporation temperature. You can see the set, it's this red line. And we have also measured the valve opening degree. The interesting thing is that as soon as we decrease the superheat, we can see that the temperature of the air inside the cabinet drops. It drops from 3 degrees down to 1 degree. So the system is performing much better. And it's performing better with a low superheat even if we increase the evaporation temperature. So by decreasing the superheat, we are able to increase the evaporation temperature and still get a better performance. Finally, we have merged the data of the two sites to show you the COP of the two systems month by month, and then we have plotted the same values here as a function of the outdoor temperature. We have also selected as a key performance indicator the specific energy consumption. This is the specific energy consumption, so kilowatt-hour square meter per day, average value for each month for both sides. Trento is always orange and Rome is always blue. And the global values, so kilowatt-hour per square meter per year, the Rome and the Trento site. So coming to conclusions, we can say that the MultiPACK project is demonstrating the feasibility and the performances of fully integrated CO2 systems in the South European climate. We have been monitoring systems completely, and we have a full collection of data, which is now giving us the opportunity of analyzing on one side operating conditions and on the other side to give energy performance indicator, and specific energy consumption has been presented as a key performance indicator. Thank you very much for your attention.